All right. Uh, so, Unit 1. This video is for Section 1.1. But this unit as a whole is going to be called Functions and Their Properties. And I think a lot of, maybe all of my notes packets are going to start off with just some kind of pre-chapter. Like if you look in some textbooks, they might give some some kind of real life example at the way beginning of a chapter, just to kind of set the tone about what the whole chapter is going to be about. We're not actually going to drill down at all. We're not going to drill down deep into these examples, but I decided to toss them into your notes packets. This one, one of the central principles of economics is that the value of money is not constant. It is a function of time. The value of money is a function of time. It changes with time. Or, the value of money depends on what year it is. Since fortunes are made and lost by people attempting to predict the future value of money, much attention is paid to quantitative measures like the Consumer Price Index, a basic measure of inflation in various sectors of the economy. So, a table of values, which does kind of set the tone, especially for this section. Again, moving on, we're not going to give those examples too much focus, too much time and energy. Chapter 1 overview, again taken right out of the textbook. AP Precalculus is a course about functions. There are multiple representations and the many ways they can be used to model behavior in the real world. In this chapter, we begin the study of functions that will continue throughout the course. Your previous courses have introduced you to some basic functions. These functions can be visualized using a graphing calculator, and their properties can be described using the notation and terminology that will be included in this chapter. Familiarity with this terminology will serve you well in later chapters when we explore properties of functions in greater depth. Pretty sure we're going to officially write down and officially talk about what a definition of a function is. Maybe in maybe lesson 1-2. I don't know. But at some point we're going to officially review this. But hopefully you remember kind of what a function is. Have a basic idea of a function, where there's input and output, and again, we'll get more into that as the chapter goes on. So here we go, officially starting the notes for Section 1.1, Modeling and Equation Solving. Modeling and equation solving. I wouldn't be too intimidated at all by the word modeling. I'm sure you recognize the concept of solving an equation. You've probably done that a billion times. But modeling is just like a fancy word that's going to get tossed around by this textbook a lot. It's not really that big of a deal. You've done plenty of modeling in the past. Let me kind of switch over to something like an example that we'll just use as an extra reference. You don't have this example in front of you in your notes packet. This is, I think, from the Keystone multiple choice releases back in 2017. But again, just as an example, this talks about Anna's Bakery charging a delivery fee for every order, and then also each cupcake in the order costs $1.15. This question could have easily been worded if this was an AP pre-calculus question. It could have said, model this situation with an equation, or write an equation that models this situation. We're kind of modeling things with well, one of the ways we model situations is with an equation just like this. And of course, if there's a one-time delivery fee, and y is the total cost, and x is the number of, it's got to be C. You'd multiply the number of cupcakes by $1.15, but also add $10.95. Anyway, back to the notes. So, all right, as we go here, if I end up, clicking to the next page a little too soon for you, like you didn't have enough time to write down what's on the screen currently. That's the beauty of this being a video. So please be ready and do not hesitate to pause the video or go back. Kind of goes without saying, I guess, but I'll say it. Don't hesitate to pause the video if you needed more time to write stuff down. Okay. So the first kind of models we're looking at is numerical models. Just with numbers. Spoiler alert, it's going to be like a lot of tables, like writing a table of, ordered pairs of your two variables in the relationship. We're modeling that relationship with just numbers, with a table. Mathematical model in which numbers or data are analyzed to gain insights into phenomena. Moving on. Again, if you need to pause and go back, do it. Example 1, tracking the minimum wage. So again, we're just giving you a basic table of values where we had the year and the minimum hourly wage in this column, and as well as what the purchasing power was. Not going to really go into great detail about what these numbers actually mean and stuff, but there's also a column for the purchasing power in 1996 dollars. But so a table of data, and then some pretty basic questions based on the data. In what 5-year period did the actual minimum hourly wage increase the most? Well, you could just kind of, again, these are all, as you look at this closely, it doesn't take very long to realize that these are all 5-year periods, I believe. And so you just got to figure out what the biggest jump is. Oh, I forgot. I set this up just to click my way through and not move the boxes on manually. Question B, in what year did a worker earning the minimum hourly wage enjoy the highest purchasing power? Well, that's also a pretty simple matter to kind of look and just say, well, it was 1970, where the purchasing power was $6.47. And then the last question, why these are highlighted. A worker on minimum wage in 1980 was earning nearly twice as much as a worker on minimum wage in 1970, because 160, 310. And yet there was great pressure to raise the minimum wage again. Why? Kind of a somewhat open-ended question. Sometimes it's hard to realize or hard to figure out exactly what they're looking for. This one's not that bad, but there can be questions where you're giving a written answer, and it's almost like, what do they even want with this explanation or something? But because look at the purchasing power. Purchasing power actually dropped. So yeah, you're making more, but did it really matter? Moving on. Example 2. Another table of data. This about U.S. prison population. So by year, the total, so 329,000 people were in prison total in 1980. That was around the time I was born. Most of those were males, but 13,000 approximately were, again, I'm assuming this is an approximation, not exactly 13,000 to the person, but about 13,000 were female. Anyway, yada 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 in the table, bunch of data. And I just kind of said that. And okay, so here's the question. is the proportion of female prisoners increasing? Is the proportion increasing? Obviously, the number is increasing, but is that the same as is the proportion of female prisoners increasing? Well, that basically means the percentage. So essentially, we're going to want to, I don't know, calculate that, even go as far, and, nerd alert, but going as far as to actually create another column where you're kind of neatly writing down all the percentages. So again, what am I doing? I'm in such a habit of manually moving the boxes by dragging. Anyway, so in 1980, how do we figure out the percentage of the total that were female? Well, you just got to do 13 divided by the total, 13,000 females divided by the grand total. That'll get you a decimal, which you can then easily turn into a percent. Hopefully, that's not making your head spin with how long ago the last time you did this kind of percent, calculation was, but there we go. The rest of these, in 1985, 23,000 out of 502,000 ends up being 4.6%. In 1990, the 44,000 out of that total, 5.7% was females. Yada, yada, yada. So, again, it's like how extensive of an answer are they looking for here? Was it increasing? What do you just say, like, yes? Yes, it is clearly increasing. The next kind of model would be algebraic. And there's that. Mathematical model. I'm going to try not to literally read to you, like story time on the magic carpet. But there's that. Basically, I would highlight, the word formulas. Wouldn't be surprised if there would have been the word equation in this definition. Uses formulas, formulas, equations. Example 3, based on that. A pizzeria sells a rectangular pizza with those dimensions for the same price as its large, round, obviously circular pizza, 24 inches in diameter. If both pizzas are oh, I love this. Man, that's really covering your bases. If both pizzas, just making sure that's being said. If both pizzas are the same thickness, if that's not a factor, which option gives you the most pizza for the money? Well, think about it. And again, always feel free, because I'm probably not going to pause too much to give you like wait time or time to do these things on your own. So always feel free to pause really quick if you want on all these examples to kind of figure it out for yourself before, or at least think about it, predict what I'm going to do. But anyway, so here we go. What we're going to do is basically, again, there I go again. It's hard to break. We're going to calculate how much area each one has, and just compare the areas. If thickness is not a factor, basically, otherwise we'd be comparing the volume of the pizza, but if the thickness is the same, is not really something to worry about being different. All we really need to do is calculate the area. So remember, this might be going way back, but the area of a rectangle, you do length times width. So that would be 432 square inches of pizza in the rectangular one. And then do you remember the area of a circle? How we do the area, what formula for area of a circle? Pi r squared. And then remember, they're giving you the diameter. So the radius would be 12 with a diameter of 24. And so obviously the pizza that gives you the most bang for your buck is the circular pizza. Let me just double check that. Yeah, 452.4 square inches. Exploration 1. I don't even know if we're going to be doing this in class, let alone like in this video. So feel free to look that over if you want, but I'm going to skip that. Again, we might not even very likely we're not even going to like spend any time on that in class going through it. And then there's graphical models, like modeling a situation with a graph. You've done that before. It's visual. It's visible. It's visual. It's a visible representation. Okay, so feel free to pause as needed to write that down, but I'm moving on. I am not very patient right now. Example 4. Galileo spent a good deal of time rolling balls down inclined planes carefully, like ramps, carefully recording the distance they traveled as a function of elapsed time. His experiments are commonly repeated in physics classes today, so it is easy to reproduce the typical data of Galilean data. So here's a table of data. What graphical model fits the data? Can you find an algebraic model? So what graphical model fits the data? And again, it's hard to, sometimes not very clear how, extensive they want you to go with answering this kind of question. It might just very well be, will this data make a line? Will it make some kind of curve, like a parabola? Remember parabolas? So that's what this question is primarily, or maybe fully, like that's what it's getting at least primarily getting at. What's the graphical model? What kind of graph does it make? A line, a curve, and other things that we probably haven't learned yet. But anyway, those are the main two. Okay, hopefully I didn't freak you out there with, wait, what don't we know? The big two are linear and quadratic for answering questions like this. So let's plot the data, and I think in your notes, literally it's just a blank grid. So we literally have to label the axes, and remember, like the independent variable, the one that's a little more independent, that's usually your x, and like horizontal, x-axis, horizontal. And then whichever variable is more dependent on the other one, on the other variable, that normally gets the vertical, or the y-axis. So anyway, just skipping ahead here, based on these numbers, I labeled it as just 1, 2, 3, 4, 5, 6, 7, 8, looking at those numbers. And then I labeled them by 2. I didn't actually write 2 and 6 and 10, but these are all going by 2 so that we can get to 48 and kind of, spread out the numbers real good. So that's how I labeled and scaled, I guess might be a word, my x-axis and y-axis. And then once you go ahead and plot all these points, take a look at that. How do you like them apples? Would you call this a line? No. Looks like a parabola. Okay. And again, I'm just kind of pushing through here. Here's what we do when it comes to an algebraic model, right? So just brace yourself, because I'm getting like pretty heavy, pretty fast here with things that you might not remember very clearly from Algebra 2 class. Okay, so this is a parabola. Okay, or it looks like it, pretty darn close, as best you can tell, right? It's not a line, it looks like a parabola. So those equations they had x squared in it, Do you remember how like the full standard form of a parabola would have been like y equals, something x squared, like normally it was ax squared plus something x, normally bx, plus c. So y equals ax squared plus bx plus c. Even if b was 0 and or c was 0, that was the form. Ax squared plus bx plus c. But if you remember anything about those equations and how they related to the graph, if the parabola has a vertex, which this one appears to have a vertex right on the origin, okay, then here we go, ready? Then it would just be, well, I'm using K here, but that's okay. Then that would be the extent of the equation. There wouldn't be a plus anything x plus c, It would just be something x squared. So that's where we can kind of start. It's just that, is this the, like your basic parent parabola where all it is literally y equals x squared or y equals 1x squared? I don't know. But it's y equals something x squared. And here's what we can do. And you can just kind of throwing in more, throwing in variables that more relate to the situation. Instead of x, t, for time. And instead of y, we have d for distance traveled, right? So I'm throwing in that ordered pair, okay? It's just one of my ordered pairs, okay? It's probably the best one to use, furthest away from the origin, I guess. And when I throw that in, it'll allow me to solve for k, which I get as about 0.75 or exactly 0.75. And then I can say, well, then that makes my equation, y equals 0.75 x squared, or you could use these different variables like I am here. D equals 0.75 t squared. So that's my algebraic model. That's the equation that models this table. And we use the graph to help us there. Next example. Back to the females in prison. Let's see, what does it want to model? Model this growth graphically and use the graphical model to suggest an algebraic model. Where it's like, hey, maybe it'll be linear, maybe it'll be quadratic. Let's see. Again, first we have to kind of scale this, and so that would be the years after 1980, and I'm going by fives. It makes sense. And then this would be the percentage, and I'm just going by ones. And then when we plot the data, there we go. So looks like, again, as best you can tell, this is not an exact science, at least for now. You'd look at that and go, it's making like a line. So if I want to come up with the algebraic model, wouldn't it be like something like y equals mx plus b, or ax plus by equals c, like something where it's not x squared in the equation, it's just x. That's linear. So I am just doing, you've done this before, I'm figuring out the slope using this point and this point, the points that are the furthest apart. It's probably pretty good business, pretty good strategy to pick those 2 points rather than, can you imagine picking, like what if I picked these 2 points to make my line? That line is looking like this, which does not really fit the data too great. So picking these points that are the farthest apart, that was pretty smart. And again, you've done this a lot. That's the slope, and then actually, you could take advantage of the fact that if it's 0, 3.9, that's literally your what? Y-intercept. So there's my equation. What's here to say? Oh, it's a line. And again, if you want to use like these actual variables here instead of x and y, you can use t and f. All the better, I guess. Once again, probably not even going to do this in class. Probably won't have the time, but you can look through it if you want. Zero factor property. This is not new either. The concept that if a product, which is a multiplication answer, the product of real numbers is 0 if and only if at least one of those numbers, factors, in the product is what? The only way to multiply two numbers together and get 0 is if at least one of those numbers is 0. That's actually a property that they write in textbooks to make that official, I guess. Or I don't know. Example 6. Solving an equation algebraically. Okay. Maybe the first of a number of times you'll hear me say this over the course of this course. But whenever you're solving for x, if you remember way back in the early days when you were just kids of solving for x, you were just in the business of, well, let's just get x by itself. That's all you really needed to do in those early days. Just do whatever you had to do to both sides of the equation to eventually get x by itself. But in Algebra 2, you learned eventually that there was equations that you needed to solve algebraically, that you couldn't just get x by itself. And the strategy became, or at least plan A, like your initial plan for solving was to what? Whenever you can't just get x by itself, what you want to do is set the entire thing equal to 0. So get everything on one side, which makes the other side, 0. Set everything equal to 0. And try to do what to this side? Starts with an F. Factor. Which is a can of worms. The world of factoring, the whole topic of factoring. But hopefully this is somewhat, clear in your memory banks. But we're going to try to factor this. And we're going to do first by trying a GCF, which there is one. So that's factoring by GCF. And then if you remember back in Algebra 2, sometimes you bring out a GCF and you can factor this bubble, this factor, like again, by unfoil. Maybe that means something to you, the term unfoil. But or breaking it up into two binomial factors. And oh man, right out of the gate, a juicy one. So when there's a number out in front, like this 6 out in here, unfoil, or factoring into two binomials, that gets way more complicated, or at least a little more complicated, sometimes way more complicated. Good thing there are special tricks, like at this school or in this classroom, called the Phoenix method. Maybe you remember the Phoenix method, where you multiply the 6 to the other end, and you get 60, and then you can unfoil pretty simply. But with the Phoenix method, once you do that, you have to bring the Phoenix back to life like that by dividing it in. And then you take both fractions and you reduce them if you can. And then you bump up any leftover denominator, okay? So the 2 bumps up to the x, and the 3 bumps up to the x. So here is your final, all that just to factor. But what do you do once it's factored? Again, we're trying to solve. Okay, we got everything equal to 0 on one side, right? And then you factor, but then what do you do after that? This is like a multi kind of phase strategy. You might call this phase 3. Set equal to 0, phase 1, phase 2, factor, phase 3, set all the individual factors equal to 0 separately. Because again, this refers back to the 0 product property. Yeah? If all these multiplied together equals 0, well then x would equal 0, or this bubble would equal 0 in disguise, or this bubble factor would equal 0 in disguise. And that eventually leads to 3 different answers. Almost done, I think. But that was a big example, right? Recalling how to solve quadratic equations or even equations that are power 3. I mean, this ended up being basically solving a quadratic for the most part. But yeah, solving equations algebraically where you can't just get x by itself like you would want. Next, maybe the last example. Feels like it to me. I don't know. Solving an equation, comparing methods. Okay, so algebraically, we just talked about this. Maybe this can just fast track. Again, can we just get x by itself? No. Like we got an x squared term and an x term. That kind of throws a wrench in the gears kind of thing. So what we're going to do is go to a more advanced strategy learned in Algebra 2. And we just reviewed just now, a few minutes ago. Or over the last few minutes. We're going to set everything equal to 0. And then we're going to try to factor. We're going to try to factor. I wonder if the factoring will work out in this example. Let's see. Okay, well this might be, okay, there's no GCF. Remember, you always try a GCF first. There's no greatest common factor with these 3 terms. So will this unfoil? Now there's no special, number out in front here. So I mean, this will potentially be more basic unfoil, but you would need there to be 2 numbers that multiply to make -10, but they would also then add or combine to make +4. -1 and +10, +1, -10, 2 and 5. No. So this doesn't factor. Okay, so here's a big question to kind of, as we near the end of this whole lesson, maybe like the last big question of this lesson, basically, last big thing to review. What do we do now? If we can't just factor, what's the backup plan when it's a quadratic equation that we're solving? Do you remember that there's literally a quadratic formula? Remember that? Huh? Hopefully at least a little bit. Do you remember how there's a song to help you remember the formula? That goes like opposite of b plus or minus square root of b squared minus 4ac, b squared minus 4ac all over 2a. This would be negative b. b is 4. Remember how this goes? ax squared plus bx plus c, which makes c -10. It makes b +4, and it makes a +1. So opposite of b, b is +4. Hey, I might as well throw in some reminders in general about the quadratic formula, since it's probably a little bit rusty with you. Be very careful, because whenever b is negative, people screw that up a lot. Especially when it comes to like squaring a negative. Remember, you have to like put it in parentheses. If this was a -4, then it, when we square -4, we should end up getting like +16. So people mess that up when b is negative. They also mess it up when c is negative, because we have like a minus here and then a negative here. So just don't screw up the negatives. Otherwise, it's just a formula. Formulas are like free answers. Okay, geez, another can of worms. Wow. A lot of potential tangents and cans of worms we can open up as we try to finish this lesson. What do I mean by that? Well, once you calculate what's called the determinant, or not the discriminant, the discriminant here, the part under the square root, it's like, what do you do from here? We end up getting the square root of 56. Do we approximate that? Because the square root of 56 obviously is not a nice, whole number. So what do? If you recall, we normally don't approximate it into a decimal. We usually simplify it if we can, and I think this does simplify. So technically, again, this is what I was talking about with the whole potential can of worms. Like if this was like the square root of 13 or the square root of 5, we'd be just done. But in actuality, with this being the square root of 56, and I'm pretty sure the square root of 56 simplifies, we would technically want to keep this going. But for right now, let's just, I don't know, let's just kind of not go too crazy with this example for now. So this is the answer, and again, there's two answers here. One answer where you go with the plus, negative 4 plus root 56 over 2. And the other answer is if you go with the minus, negative 4 minus root 56 all over 2. Remember, it's literally negative 4 plus or minus root 56 all divided by 2. Okay? Quadratic formula. Last thing. Solving graphically. Okay? If you remember, maybe in Algebra 2, this is almost like an ultimate like secret weapon, ultimate like life hack or math hack. If you have access to graphing technology, whether it's your graphing calculator or Desmos.com, this is probably straight from Desmos.com here, okay? I don't know if I saw any screenshots of, never mind. From Desmos, no, I think this is the first time. So graphing calculator or Desmos.com, the ultimate math hack in solving like most equations, okay, is if you graph it, if you set it all equal to 0, okay, and then graph it as, this is probably not written down, so maybe in your notes you can write y equals, sorry I'm writing with my mouse, might end up a little messy, plus 4x minus 10. So you want to, oh geez, that's bad. So you want to set this equal to 0 anyway, but you graph it as y equals x squared plus 4x minus 10, and the answers, if there are any like real answers, sorry to drop that bomb in there too, as we review a lot, but any real answer, real solution to the equation will just pop up as x-intercepts. So I don't know if you want to make a note of that. Okay, whenever you graph it as y equals, the solutions, any real solutions anyway, as opposed to imaginary, just dropping bombs all over the place. Dropping memory bombs. But anyway, so any real answer will pop up as an x-intercept, which on Desmos just will automatically be highlighted, and you can click on them and stuff. But so Desmos is really, really quite nice. Otherwise, on a graphing calculator like a TI-83 or something, you'd probably be in store for like a lot of zooming and zooming in and putting like your cursor over the intersection point and like zooming in a bunch of times to try to get like a pretty good answer that's accurate. But anyway, we did it. That will do it for section 1.1 notes.